In the last video, we showed that the fn's, the distribution functions, converge uniformly to some function capital F. In this video, we shall first show that this capital F is a CDF itself. Once I prove this CDF will define a distribution, and that distribution we shall call the Cantor distribution. Now, in order to show that it is a CDF, we need to show certain properties. The first property is that F must be non-decreasing. Now, that should be obvious from the fact that each Fn being a CDF, each Fn is non-decreasing, and since I am taking limit, that must also be non-decreasing. More precisely, suppose I take two real numbers a less than b, then I need to show that Fa is less than or equal to Fb. Now, what is the definition of Fa? It is the limit of Fn is. Similarly, Fb is the limit of Fnb. Now, since Fn's are themselves CDF, so these are non-decreasing. As a result, we always have this inequality. So, when I take limit of this and this, in the limit also the same inequality will be preserved. As a result, we shall get Fa less than or equal to Fb. Next, we need to show that limit of fx as x goes to minus infinity is 0 and x goes to plus infinity is 1. Now, that one is absolutely trivial here because I know that all my fn's are actually of this form, such that it is 0 to the left of 0 and 1 to the right of 1, and all the zigzag business occurs inside 0 to 1. So, when I take limit, obviously my fx is also 0 all the way to the left of 0. So, this just holds trivially. Similarly, it is 1 all the way to the right of 1. So, this also holds trivially. The third condition that I need to show is that f is right continuous. Now, that is just obvious because all my fn's are actually continuous, not just right continuous, because they are obtained from density. It is a uniform distribution over certain intervals. And we know that uniform limit of continuous functions must be continuous. So, if you take a sequence of functions, all of them are continuous and their uniform limit exists, then the limit must be continuous. So, f is actually not just continuous, it actually happens to be, it is not just right continuous, it happens to be continuous. So, in particular, right continuous as well. Now, we know that a function is a CDF if and only if it satisfies all these three conditions. So, we can say that capital F is a CDF. So, this really gives me a distribution, that is thanks to the fundamental theorem of probability, which says any function which satisfies these conditions must correspond to a distribution. You can have a random variable such that this will be the CDF of that random variable. And that distribution is what we define as the Cantor distribution. So, now we have finally defined Cantor distribution in a rigorous way. The definition that we gave of the Cantor distribution was pretty complicated and roundabout. Now, in certain books you find another definition which is not a real proper definition, which uses the concept of the Cantor set. Now, the Cantor set is something that is important in its own right, and it is defined like this. You start with the unit interval, closed unit interval. I give it a name, I call it S0. And then we proceed exactly the way we did. We remove the middle 1/3 and this resulting set we called S1. We again remove the middle 1/3, always removing the open middle 1/3. this set consisting of union of 4 things we call S2, exactly as we did earlier. Now we keep on doing this forever, meaning we take limit of Sn as n goes to infinity. Now these things are all set. So what do I mean by limit of Sn? By this we mean that, observe that S1 sits inside S0, S2 sits inside S2, S1 and so on. So by the limit we mean just taking intersection. That is defined to be the Cantor set, which I denote here by capital C. Now these books define the Cantor distribution as the uniform distribution on C. This just sounds like a very meaningful definition until you notice that uniform, the word uniform in this context is not well defined. What does it mean? We have already talked about uniform distribution for a finite set. For example, if our set, instead of capital C, it is just this double-turned set head-tail, we understand what is meant by uniform distribution. We count the number of elements in our set, here it is 2, and we give equal probability to each one of them, half-half. That's uniform distribution. But this prescription works only for finite sets. If the set is infinite, as in case of C, which is an infinite set, we cannot talk about uniform distribution in this sense. Well, we have seen also another definition of uniform distribution in presence of density. For instance, when we talked about uniform 0, 1, we meant that you take the set 0 to 1. Of course, it is an infinite set, an uncountably infinite set. We cannot say that each point has equal probability. Anyway, each of them has probability 0. But that is true about any continuous distribution. So what is uniform about it? We gave it a density. And the density vanishes outside this set. And it is equal to, so it is some flat density. That is the important thing. In this case, since this has length 1 and the total area must be 1, so the height is also 1. So the important thing is that it must be a constant density over that set. That prescription also does not work here because, as we are going to see in the next video, this distribution that we have defined really does not admit a density. So you see, we have only 2 ways of making this word precise, this word uniform precise. One is when we have PMF over a finite set, or when we have a density. In this case, C does not satisfy either of the 2 conditions. Cantor distribution does not satisfy the condition that it is not supported on a finite set and it does not admit a density. We have not yet shown that it does not admit a density. We shall do that in the next video. But the term uniform, therefore, is still undefined in this context. So that is why we cannot use this as the definition. That is why we defined it in that roundabout way. We first defined uniform distributions over each of the Sn's, and then we took the uniform limit of the distribution functions. But it is true that this does remain a pretty intuitive way of thinking about it, because obviously if a random variable has Cantor distribution, it must take only value in C, because obviously it cannot take value in the middle 1/3, because I had removed it in the very first step. It cannot take values in these things also, because I had removed that in the second step. So it must take values in C, and from the way we constructed it, we are always taking uniform distributions at every step. So no point gets more or less important than any other point. So uniform is a good intuitive way of thinking about the distribution, but this is not a valid mathematical definition. In this exercise, I give you a random variable x which has Cantor distribution. I want you to find out the probability that x lies between 1/9 to 8/9. In other words, I want you to find f of 8/9 minus f of 1/9. Because f is a continuous CDF, so it doesn't really matter whether I am putting round bracket or square bracket. So try to find this out. Remember that this is limit of the fn's, this is also limit of the fn's, and you should see the pattern.